Hello everyone, hope you're all doing well. We're now beginning our second lecture series on section 7.2 for the review of homework on the dot product. All right, let's get into it. So some preliminaries to set up. One is, I think the most important, is how to interpret the dot product. So when I first learned the dot product, I thought of it as like a very abstract operation for vectors. And I didn't really get a handle on as to what it did. Now I can pretty confidently say that the best way, in my opinion, to interpret the dot product is as projection. So imagine you have two vectors, v and u. You can imagine the dot product as a sort of measure on how much v is capable of casting a shadow onto u. So you can imagine some light source shining, and the shadow cast is sort of, in a sense, the dot product. It's a measure of this shadow. So the dot product. I'll do it. It's not really a definition per se, but more so like an intuition on how it is. It's a measure of projection. And this obviously entails that it's going to be angle dependent between the two vectors. Always remember, by the way, that the angle we take when applying the dot product operation is when the vectors are tail to tail. That's really important. Okay, good. And then there's the formulas that you should know for how to use the dot product. So the geometric formula for v dot u would be magnitude of v, magnitude of u, cos theta, the angle between. That's the geometric. And then the algebraic or Cartesian formula would be component-wise multiplication. So v1, u1 plus v2, u2. You might sometimes see me write vx, ux, vy, uy. They mean the same thing. Sometimes people use either or. Okay. That's good. Sets up our groundwork. All right. Let's begin. So, question 1. Calculate the dot product for each pair of vectors. Round answers to one decimal place. So for 1a, we have the vectors a and b. In this case, we're going to be using only the geometric dot product. Cosine of theta is going to be 70 times 115. Oh, sorry. Cosine of 70 degrees. We'll calculate all of these at the end, the decimal values. For b, we have c times d, magnitude of c, magnitude of d, cosine theta. In this case, we have 8 times 12, cosine of 150. For c, we have, I think that says c times c dot f. Can't really read that, but I think that's what it says. And then we have 150 times 200, cosine of 90. And then d, we have g times h, or g dot h, sorry. I always never say times when you're dealing with vectors. It's always the only sort of synonymous operation with multiplication for vectors is the dot product, or you'll learn later on the cross product. So then g times h, cosine of theta, 5,000, 4,500, cosine of 180. Okay, and then now let's calculate all these guys. So 70 times 115, cosine 70, cosine 70, we get 2,753.3. Okay, 8 times 12, cosine 150, minus 83.13, minus 83, I guess, 0.1. And notice that the answer here is negative, which makes sense, because if some light source was to cast a shadow onto vector D, the projection would not be onto C directly, but onto its negative counterpart, negative C. The anti-parallel vector, in a sense. Good. Minus 83.1. And then we have 150 times 200 cosine of 90, which we know is going to be 0. And again, that intuitively makes sense. A shadow cast onto the vector F, or a light source directly overhead of F, would cast no shadow onto C, which makes sense. I guess I'll keep it there, actually. And then we have 5,000 times 4,500, cosine of 180, and we get a really large number. All right, good. That completes 1. Let's move on to 2. I'm not going to do all of 2. I'll do some select exercises. Let's do A, C, and E. So we have magnitude of U. Well, I guess I should first write the formula down. So we have U dot V. And again, I'll just calculate all the values at the end. Magnitude of U, magnitude of V, cosine of 30 degrees. This is just plug and chug away into your calculator type of business. Six times 10. C. F dot G, magnitude of F, magnitude of G, and then we have cosine of theta again, and we have 5.8, 13.4. Sorry, these should be in brackets. Cosine of 180, and then E, A dot B, $850 times 400. This work is quite tedious, it's all just plugging into your calculator. Nothing really, no really technical algebra involved here. Six times 10. cosine of 30. We get 51.96, 5.8 times 13.4 cosine of 180 minus 70.72, 850 times 400 cosine of 58, 180,172.54. Good. Okay, let's move on to question 3. So question 3, it asks us to use the properties of the dot product to expand and simplify each of the following, where K and L are elements of the real numbers. Okay, so I listed the properties of the dot product right here. So A, I'm going to do all of these. We have U dot K U plus V. So I'm not going to say the specific property I'm using. I'm just going to list the number. So I'll say 1, 2, or 3. So I don't want to have to keep saying their names. Okay, so like so we can use 3, the distributed property here. We're going to get I guess I should do it like this. So we're gonna get I guess we should also use the associative property alongside of it. So in combination we have U dot KU plus U dot V. Seems about right. I guess you can if you wanted to move this scalar outside completely. So this would be using by 3 K U dot U plus U dot V. That's by 2. I move the scalar out. And then what we can actually do if you wanted to make this look even nicer, I don't know what the textbook solution is, but you could do K. This is actually K U squared plus U dot V. All right. Moving on. B. So this is by 4, I guess. B. KU minus V time dot LV. Okay. So we can use the distributive property to distribute LV in for each term. So I'm actually going to do it like this. So KL U dot V, that's using, and then L V dot V. All right. That's, I'm using in combination 2 and 3 all in one step. And then this becomes KL U dot V minus L V squared. Okay. That's by 4. C. U minus V dot U minus V. So this is another round of distributing. U, and then minus U minus V dot minus V. All right. This is by 3. I'm just splitting up this binomial vector here. And then we get, we get U dot U minus V dot U. That's from this guy. And then this guy will give us minus minus V dot U plus V dot V. Because the minuses cancel. Okay, so then you're left with U. U squared minus 2U dot V plus V squared. Okay, yep, that makes sense. You're just kind of, you're foiling. It is, in a sense, like it does boil down to just foiling these two vectors when you're dotting them. But the operations, the properties of the dot product you're using are actually distributivity. Okay, good. And then D, we have U plus V dot W plus X. U plus V dot W plus X. Okay. For this problem, we get U plus V dot W plus U plus V dot X. Okay, so then we have U dot W plus V dot W plus U dot X plus V dot X. Yep, makes sense. Okay, 4. Moving on to 4 now. So from 4, I'll do A, D, and F. So A, we have U dot V. And this time I'm going to use the algebraic formula. So we're going to have 2 times 3 plus 4 times -1, which is going to be 6 plus 4 times -1, 2. And now let's do C, or let's do D actually. We have P dot Q. And then here we get negative 6 times 9 plus 2 times 1. Negative 52. All right. And let's do f then. So for f, we have the vectors s and t. S is 4i plus j. This is equal to... This in its component, its compact component form, which would be 4 plus 4, 1. And then we have the vector t minus I minus j. Which is going to be minus 1, minus 1. So now we can easily do the dot product between the two, which is just 4 times negative 1 plus 1 times negative 1, which results in 4 times negative 1 plus 1 times negative 1, negative 5. Good. All right. Now I don't want to smush everything on one page, so I'll do 5. Maybe I can fit 5. Yeah, 2. I think I'll just do them on the side here. Okay, so 5. We have, for 5a, we have u dot v dot w. This operation will result in a scalar. This operation here will result in a... Oh, wrong one. And then we'll have a scalar dot some vector, which is not allowed. So A is not possible. That immediately removes A from the options. Okay, so we know A is not possible. I guess I'll do a little x. Okay, B. So for B, we have this operation here will result in a scalar. And then we have a scalar inside absolute value bars, which is perfectly fine. That'll just take the positive value of whatever the scalar is. So that's good. That's fine. It's allowed, actually. Good. And then this next guy. So we have u, and then this dot product inside. Remember, we're using BEDMAS, order of operations. This will result in a scalar when you perform this. And this multiplied by a vector is just scalar multiplication. So that's allowed. That's perfectly fine as well. Nothing wrong with that. This is perfectly allowed. This is just the magnitude of the vector squared. So that's perfectly fine for D. E is not allowed because E would be like V and then V squared. But there's no operation that's equivalent to multiplication just for vectors because since they have a direction and a magnitude, you can either do the dot product or the cross product. So this is not allowed. I guess I should note, even though we've done this question, that the dot product needs two vectors to tango, in a sense. You can't have a vector and a scalar. You have to have two vectors. Okay, this one is also perfectly feasible because it'll result in a scalar squared. Perfectly fine. So we're good. That's about it for the first part of this video series. I will see you next time where I complete 4 more problems in this section. Thank you so much, guys.